All right, so when you, oops, I gotta move that out of the way. When you guys inhale, the volume in your chest cavity increases. So everybody take a deep breath. And you feel your chest increase. So it's expanding to take in the extra air, right? And when you exhale, your chest will cave back in. So when you do that, your volume of air in your lungs is changing. When you inhale, you're letting a lot of air in. Your body takes the oxygen out of the air. And then when you breathe out, you're breathing out the extra air along with some carbon dioxide. Okay? Now, when you do that, this changes the volume, the temperature, and the pressure of the particles, and it's a predictable behavior of a gas. Okay? So when you breathe in, take your hand, blow on your hand. It comes out hot, right? It's warmer than the air that you breathe in. That's because a chemical process takes place. When you breathe, you're putting oxygen into your blood. That blood does a bunch of stuff. Basically, it provides your body with energy to some degree. It does a lot of other things too, but the main one is you use that oxygen to facilitate energy consumption in your body. That gives off heat, right? Remember we talked about that. Heat and energy are related. Heat is a type of energy. So what causes gas pressure in a closed container? Well, pressure is a result of the force distributed over an area. Look at the board. See how those gas particles are moving around? They're bumping into the sides of the container. Now, if I put more molecules into that container, it's going to push up against the sides of the container. Collision between the particles of gas and the walls of the container cause the pressure in a closed container. So when you're moving a hockey puck, you exert pressure on any objects that it hits, right? So think of a hockey puck, or think of air hockey specifically. When that thing hits the side of the wall, it pushes up against the wall. Well, it's a very similar thing that takes place with air molecules in a container or air molecules in your lungs. Okay? The faster the puck is traveling, the greater the force of the puck on the glass. A greater force means more pressure. The smaller the area of impact, the greater the pressure. If the edge of the puck hits the glass, it exerts more pressure than the face of the puck hits the glass. So they're talking about a very thin edge, right, on the puck. All that momentum, all that energy gets channeled into a very small area. But if I take the circle part of the puck and I slam it up against the wall, that has a different impact. So the SI unit of pressure is derived from the SI units of force and area. Force is measured in newtons. Area is measured in meters squared. The SI unit for pressure is Pascal, and PA is shorthand for newtons per square meter. So it's N over M squared. Scientists often express larger amounts of pressure in kilopascals, or lowercase k, capital PA, is equal to 1,000 pascals. Okay? So helium atoms in a balloon are constantly moving. There are more than 10 to the positive 22 helium atoms in a balloon. So that's a 1 with 22 zeros after it. That's a lot of zeros. Set it right there, please. When many of those particles collide with the walls of the container at the same time, they produce measurable pressure. Those helium molecules are traveling back and forth in the balloon, and they're pushing up against the walls. And if you put more molecules in there, the balloon will expand. Okay? The speed of those particles and their mass also affect the pressure. So what factors affect gas pressure? And factors that affect the pressure of an enclosed gas are the temperature, the volume, and the number of particles. So they're related. Okay? So raising the temperature will increase the pressure if the volume of the gas and the number of particles are constant. A firefighter is using a pressure gauge to check the air pressure in the fire truck tire. Okay? If he checks the tire again after a long drive on the highway, he will find that the pressure is increased. The motion of the tire on the highway heats the tires and increases the pressure. As the temperature rises, the average kinetic energy of the particles also increases. With an increase in kinetic energy, the particles move faster and collide more often with the inner walls of the tire. Faster moving particles hit the walls with a greater force. More collisions and increased force cause the pressure of the air in the tires to rise. Okay? So there's that relationship again of heat energy and kinetic energy. Basically, the particles inside of the tire absorb the heat energy, convert it to kinetic energy, and they move faster, and that increases the pressure. So reducing the volume of the gas increases its pressure if the temperature of the gas and the number of particles are constant. Let me read that again because it's a little bit counterintuitive. Reducing the volume of the gas increases the pressure if the temperature of the gas and the number of particles are constant. Let's figure out why. Twist the cap off of a plastic bottle and then squeeze it. What happens? The volume of the bottle begins to decrease. As the volume decreases, the particles of the trapped air collide more often with the walls of the bottle. The pressure in the bottle increases. So here's an example or diagram of when we're inhaling and when we're exhaling. Movement from the muscle called the diaphragm changes the volume in your chest cavity. The volume increases when you inhale. The pressure decreases and air flows into your lungs. So when there isn't any air in my lungs, but when my diaphragm moves, I open up my lungs. And when I open up my lungs, the air particles outside of my lungs, they're able to go in. They're able to come in because the pressure decreases and the air flows into my lungs. The volume decreases when I exhale. The pressure increases and the air flows from your lungs. In other words, I have to force the air out of my lungs. So when I exhale, that's where the pressure comes from. Because now my diaphragm and my body are going to try to close my lungs and it has this extra air in it. So there's an increase in pressure in my lungs, which is counterintuitive, right? You would think that the air coming in would increase the pressure. Not really. When I go to breathe out, I'm increasing the pressure. I'm forcing those particles that are moving inside of my lungs out through my windpipe, right? Out through my nose or mouth. But I'm putting pressure because they're bouncing around all over, and now I've decreased the volume. So there's less room for those particles to move around. Increasing the number of particles will increase the pressure of the gas if the temperature and the volume are constant. So there's three things that we're measuring. But what we're really checking out is if two of the things remain constant, what happens to the other thing? We're really measuring four things, right? Temperature, volume, pressure. We're actually measuring three things, but there's a relationship between those, okay? So this French physicist, we'll just say Jacques Charles, collected data on the relationship between the temperature and the volume of gases, right? It's called Charles' law. The graph of the data showed a direct relationship between the volume of the gas and the temperature of the gas. Okay? So Charles' law basically shows a trend, right? And the extended graph beyond the measured data define the temperature that will produce a volume of 0. So here's a problem where we're trying to figure out. But the temperature at a point where the line crosses the x-axis is negative 273 degrees. So if I extend that line down, it crosses at exactly negative 273 degrees. And if you guys don't remember, that is that one phase, the Bose-Einstein I can't say the word. I always want to say condensation, and then particle. There we go. But that's where motion stops, right? That's where motion stops, is at that temperature. Well, that's no accident. This is also the temperature that's equal to 0 Kelvin. The temperature of 0 Kelvin is an absolute zero. Kinetic energy stops at 273 degrees. Does that make sense? So just like if I add heat energy to an electron and it gets faster and it moves the atoms and the atoms move faster. If I remove that heat energy, they slow down. So according to Charles' law, the volume over the temperature is proportional to a change in volume over a change in temperature. Because there's a relationship, a proportional relationship between the volume and temperature in a container where the pressure is constant. Boyle's law is a similar situation, and he describes the relationship between the pressure and the volume of a gas. The graph shows an inverse relationship between the volume of the gas and the pressure. So this is not a direct variation, it's an inverse relation. And so basically, as the volume increases, the pressure decreases. Now notice it's the same number of particles. Have you ever taken a balloon that has a little bit of air in it and like stretched it out? Doesn't the balloon kind of suck in? That's because there's a decrease in pressure. The pressure on the outside is greater than the pressure on the inside. Again, this is counterintuitive. If there's no way for more particles to get in there, then this will be what happens. So this has a curve which is an inverse proportion. I don't know if you guys remember, but 1 over x graphs differently than mx plus b. This graph here is a linear relationship. This graph here is an inverse. We would call this in algebra a direct variation, and we would call this in algebra an inverse variation. Y equals x versus y equals 1 over x. Plus, there's other numbers that come into it. So then this one is going to be the initial pressure times the initial volume should be equal to the product of the final pressure and the final volume. Notice that the temperature is constant. So now the last one is the combined gas law, and this one is putting them both together. In other words, that the initial pressure times the initial volume divided by the initial temperature should be equal to the final pressure times the final volume over the final time. And we're going to do a worksheet on that today. So let's look at this example. A cylinder contains air pressure of 100 kilopascals and has a volume of 0.75 liters. The pressure is increased to 300 kilopascals. The temperature does not change. Find the new volume. So we're given some information. The initial pressure is 100 kilopascals. The final pressure is 300 pascals. And we're given the initial volume is 0.75 liters. So what is it that we're trying to figure out? Well, we're trying to figure out what the second volume is. The question specifically says, find the final volume. Well, that's V sub 2, right? So now when you look at that, you can cancel out the variable that does not change and rearrange the expression to solve the volume, the second volume, and replace each variable with the known variable. Okay? So in other words, if I take this first equation and solve for v squared, the only thing I'm doing is algebraically dividing by both sides by p sub 2. Right? So if I divide this side by p sub 2 and I divide this side by p sub 2, I get v2 is equal to p sub 1 times v sub 1 over p sub 2. Sorry to get all mathy on you. But you guys remember how to solve equations, right? Yeah. So anyways, then I just plug in the numbers, right? I'm going to say that the initial, this is the initial P1 times the initial volume divided by the final pressure. So the initial pressure, 100 kilopascals times the initial volume divided by the final pressure, which is kilopascals. And just like our conversions, the kilopascals are cancel out. I'm left with liters. And then when you do all the math, I get 0.25 liters. Does that seem reasonable? Well, the volume should decrease as the pressure increases. Go back to this picture here. They have a cylinder, right? If I take this cylinder and close it down, the same number of particles are still moving, but now they're closer to each other and they're bouncing into each other. So there's going to be an increase in pressure. So is that a reasonable answer? I think so. If this was 2,500 liters, that would be weird. If it was 250 liters, that would be weird. But it's not. It's within the same order of magnitude as the original volume, 0.75 liters. And then think about this too. My pressure increased by a factor of 3, where my volume decreased by a factor of 3. Right? We went from 100 kilopascals to 300. In other words, we multiplied 100 by 3, which has an effect on the volume. We took 0.75 and divided by 3. Okay? So yeah, it's definitely a reasonable answer. Here's another example. A gas has a volume of 5 liters at a pressure of 50 kilopascal. What happens to the volume when the pressure is increased to 125 kilopascal and the temperature doesn't change? Here's another example, and we're not going to go through all these examples today. I have a separate worksheet that I'll go over with you. But basically in all of these, you're going to do the same. I'm going to list, this is the initial volume. This is the initial pressure. This is the final pressure. What's the final volume? If I go to the next one, this is a change. This is the temperature. This is the pressure. This is a pressure. What is the final temperature? And so there's 3 formulas, and basically all 3 of those formulas, you're going to list what you know first, and then solve for what you don't know. They're going to give you 3 of the 4 items. And in all of those, you're going to just plug it in and do basic algebra. Multiply some numbers, divide some numbers, cancel out some things. Okay? Does anybody have any questions on this? Okay, that's it.